very much. Okay, so let's get started. First things first, we have an exam coming up, and I just want to give you some sense. Dawn sent out an email, I think yesterday, or an announcement yesterday. The exam is next Tuesday. The stuff that I am covering in class today will not be on the exam. The topics are ray optics, optical instruments, electrostatics, and that's in the standard textbook. That's chapters 18, 19, and 20. And there's a nice correspondence with the, the previous versions of the text and the open stacks on Canvas under reading instructions. I also hope that you see that I've been trying very hard to post the lecture notes beforehand, so that if you have any trouble seeing my notes through this video, they are available to you as a PDF under modules. So please take a look at that if you haven't seen that. The exam, like I said, there will be nothing on what we're covering today, which is potential. We're moving on to a new chapter. And I think Dawn gave a lot of details in her announcement, but just, you know, please bear with us. We're trying to do this for the first time, you know, in some fair way that's not too difficult for you to do, but still maintains some rigor. And the best way that we think we can do this is that it'll be on Canvas, that the day of the exam, there's going to be a 24-hour window that you can access the exam, and you'll be given the normal amount of time, which is 80 minutes to take the exam. So once you start it, you want to finish it within 80 minutes, but you can start it at any point during that 24 hours. And that's to try to accommodate people that are in different time zones. And, you know, if you have internet problems or something like that. If this still proves to be some kind of technological challenge to you, please let me or Dawn know, particularly Dawn, who's kind of organizing this. I encourage you to send her an email. And if not, you can send me an email and I'll work with you to try to find a solution. So it's the first time we're doing this. I know that you might be a little bit nervous. I'm a little bit nervous because I don't know how it's going to work out. But it's just an exam, and we'll get through it. And I really appreciate, you know, you guys have been great up until now dealing with this online stuff. So I think it'll probably be fine. And you know, both Dawn and I are very aware of the fact that, you know, you have not seen something like this before, and we will try our very best to make this, you know, as smooth as possible. The lecture videos, I'm still getting a handful of notes from people that, you know, can't access the lecture videos afterwards. I'm not sure if anybody is even looking at these, but I'm trying my best to get these up very quickly. And what happens is they get processed. I upload them, and that takes it takes about an hour. But then UNH, for some reason, processes them for many, many hours. And I think what they're doing is they're adding closed captions to them. So that takes a lot of processing time. I think what happens is they usually get up by about 5 p.m., but I don't have much control over that. I post them fairly soon, right after lecture, but it takes quite a few hours before they show up on Canvas. My alternative to that is I created a YouTube channel, Physics-Slifer, all one word, which I hope you can just Google, and I hope that just shows up. If not, please send me an email and I'll help you find that. And those ones get up fairly quickly. And for the people that just can't even access the media gallery on Canvas, I'm not sure why. Some people cannot. But for those people, well, you know, YouTube will serve as your backup. If this still is not working, just send me an email and I'll try to work with you to solve that problem. Okay, so with no further ado, let's move on. We're going to chapter 21. And this is the idea of electric potential. Historically, and including my own background as a student many moons ago, electrical potential somehow puzzled me. And I think it puzzles a lot of people why we do this. And I'm going to take some extra effort today to try to address that directly. So the first thing that we talked about, you know, in a simple case of 2-point charges, 2-point charges is the electrical force. We have a big Q and a little q here, and they could be positive or negative or whatever, but they have a force in between them that's given by, the magnitude of it is given by Coulomb's law. And then we made that a little bit more abstract, and we went to the electric field, and we say, hey, this big Q here, I put it down in space, and it creates an electric field all around it, in the region around it in space. And that electric field then over at this other point is what is the thing that influences or creates a force on this other charge Q. The math is the same. If you look at these two formulas, E equals KQ over R squared, and then F equals Q times E, all I've done is peeled out the K, Q, and R squared here and called that the electric force. So it's a bit of mathematical trickery, but it also does have some physical meaning. And it turns out to be a lot easier to deal with the electric field than it is with the Coulomb force. Now, what we're going to do is we're going to consider electrical potential and electrical potential energy. And you know, my inclination when I was a student was, why didn't we just stop at force? I got that. That was easy enough. Why keep making this more and more and more abstract? And I'm going to try to, you know, address that directly today and see if I can give you some motivation for that. So the very first reason why we do this is that force and electric fields are vector quantities. Okay, so solving any problem with anything more than the simplest charges. We looked at a one-dimensional problem with 3 particles in it, and it took us, you know, 15 minutes to work our way methodically through it. You can imagine that if I have some kind of, you know, 2-dimensional or 3-dimensional problem where I have multiple charges and they're all acting on some charge Q. So these are my sources over here, Q1, Q2, Q3, Q4. And they're acting on this guy here, and he's experiencing a force. And some of these could be positive, some of them could be negative. But if I had to then figure out what the net force on this guy is, I have to take all of these, break them down into their vector components in X, Y, and Z, right? These 3, sorry, my hand is coming in and out of subspace here, in 3 dimensions, and add them up vectorially. It's really becomes a nightmare. And this is still a simple charge distribution where I haven't even added in a big conductor or a capacitor plate or anything like that. And it really just does, I hope you'll take my word for it. It really just does become a computational nightmare. It takes so much effort just to get simple answers. So the electrical potential may at first seem like a very weird and abstract complication, but I'm trying to assure you that it really is easier. And here's my silly proof of why I think you might want to take my word for it. Is when you open up the toy or your remote control or whatever, and you look inside and you see a battery, the batteries, you know, are rated in terms of voltage. So this is a weird 9-volt battery that looks like a 3-volt battery, but it's supposed to be a battery. And you know what I'm going to tell you, the punchline to all of this before we even get to it, is that this idea of potential is what, you know, we are measuring when we talk about voltage. So if you talk about the 120 voltage in your house, if you talk about the 9-volt battery in your camera, or you know, anything like that, the battery that's in your car, the voltage rating of that's we are talking about potential. So hopefully this gives you some inclination about, you know, the world has rendered its judgment. We could have done everything in terms of coulombs, or we could have done things in terms of electric fields, but it's so much more complicated. And this is really the least worst option, this kind of idea of voltage and potential. Okay, so that's not a proof. It's not, you know, showing you anything, but it's just some indication that, you know, millions of people, millions of engineers and scientists and just regular people have had the choice before us, and they kind of defaulted to this idea of voltage. So please do bear with me. At first it might seem abstract, but it really is simpler. And the number one simple thing about it is it's not this vector quantity that we have with electric field and with forces. So let's, you know, okay, so that's just laying the groundwork. Let's actually start with this idea. I have to be clear, there's there's two things that we're talking about. One is electrical, sorry. We have the idea of electrical potential and we have electrical potential energy. I'm sorry, the words are very, very similar. And if we could go back in time, we would change this. But these are two different things. They're very similar, very closely related, but they are two different topics. So in your head, please put a pin in this. When I say electrical potential energy, I am meaning something slightly different than electrical potential. All right. So let's just hit the ground running here. So let's start with electrical potential energy. If we recall gravitational potential energy, and what's the point of gravitational potential energy? We had Newton's laws. Sorry, my phone is going off. It's home office. Things like this happen. Recall gravitational potential energy. We could deal with Newton's three laws and solve them, to get the equations of motion for something that's moving through a gravitational field. And that's pretty gnarly, especially when you have more than one particle. Even with one particle, you'd have to figure out what the forces on this ball that the guy is dropping off of the roof of a building. You'd have to figure out the acceleration. Then I want to integrate that to get the velocity and the position of the object to figure out what's going on. The power of potential energy, especially in gravitational potential energy, is we can just use conservation laws. So we have an initial state where this mass m is at a height h. It's at some initial y, and after a few seconds later, it's at some final height y final. The mass has come down here, and we can use conservation of energy. And what conservation of energy tells me is that the kinetic energy plus the potential energy in the initial state is going to be equal to the kinetic energy plus the potential energy in the final state. Kinetic energy is 1/2 mv squared, right? You guys remember that, I hope. The gravitational potential energy is mgy, and we have that in the initial state and in the final state, the final kinetic energy and the final potential energy. If I recall that the initial, I'm dropping this water balloon from the top of Demerit Hall with an initial velocity of 0. So I just let it go. I'm not pushing it down. So it has an initial velocity of 0. This term falls off, and then I have this term, this term, this term. If I gather together the potential energy terms, and I get the feeling today, I feel like I'm talking too fast. So please, again, in the comments or in the chat, just let me know if I'm going too fast, and I will try to slow down. So this term here and this term here are our potential energies. This term falls off because the V is 0, and I'm left with this, this, and this. I put these two terms together to get this guy over here, mg y initial minus y final, and this is equal to 1/2 mvf squared. The y initial minus y final is just this height h. So altogether I have mgh equals 1/2 mvf squared, and I have this final result, that all this initial potential energy, mgh, is converted as this mass falls from here to here. It's converted into this kinetic energy 1/2 mvf squared. Okay, so that's all the setup, but the actual payoff is that if I wanted to find out what the velocity is in the end, I just solve for this vf, right? This vf, if I solve for it, I have to put this on the left side, put everything else on the right side, and take the square root. I get this very simple equation, and this is a super easy equation to solve, and it's much easier than dealing with Newton's second laws and integrating and figuring out the forces and all that. So, that's either you agree with me or not, but that's to me, that's super easy compared to having to use Newton's second laws. Even though Newton's second laws might be conceptually a little bit simpler, and I might feel more comfortable with the idea of force than potential energy. So let's take this a little bit further. Let me pause just for a second here and see if there's any questions. I feel, again, you know, with this video format, I can't gauge your faces. I can't read whether, you know, you're following along or not. So I'll give a moment here to just allow you to catch up to me and give me a question in the chat if you have any. Nope. Okay. So, and feel free, you know, in the beginning, I was worried that I would be swamped with audio, like a lot of people talking at once. You guys have been super polite and super great at monitoring yourself. Please feel free to use the audio if you want to interrupt me. I don't mind, and it seems like it's going okay. So, so where are we at here? 30. I want to explore now this relationship between potential energy and work. So if we wanted to increase the gravitational potential energy of this mass, what we have to do is we have to do some work. So if I start in this initial state and the ball is at the bottom of the building, if I want to increase its gravitational potential energy, I have to lift it up. I have to lift it up and put it at some higher height, and that increases its gravitational potential. The amount of increasing gravitational potential, whoops, let me see, I'm getting some questions here. I think, yes, it is. It's Mega Man. Yes, I think this little guy up on the corner is Mega Man. I get a question from Brandon. Is that the opening of Mega Man on the NES? I do believe it is, yes. Someone else, I was wondering the same thing. Yep. James Donald says it looks like Mega Man 2. I'm not sure, but I think it is. Woo, that's all. Okay. All right. So, you know, Mega Man could be on this building and he could be throwing something off and you know, trying to investigate gravitational potential energy. So let's see. So we have this definition of gravitational potential energy, MGY. And what we're going to do is that if we want to increase the gravitational potential energy of this object, we have to do work on it, right? We're investing energy in it by doing work. And the same thing is going to happen with electrical potential energy. So electrical potential energy, what I want to do is kind of base an analogy here with that idea of oops, I'm going out of focus here. I have a mass and I raise it up to the top of the building and I do work on it, and it gives it a gravitational potential energy, or it increases its gravitational potential energy. Very similarly, if I set up a system here, I'll focus your attention please on the left-hand side, which says initial. And what I've done is I've set up a 1-volt battery, right? You know, we haven't defined volts yet, but you guys know what a 1-volt battery is. It's just, you know, you take it out of the junk drawer in your kitchen and you have a 1-volt battery or a 9-volt battery or something like that. And I attach it to 2 metal things, right? Let's say they're capacitor plates that we talked about last time. So that I create a separation of charge, and on the top plate, I'm going to have positive charge, and on the bottom plate, we're going to have negative charge. And this is kind of what a battery does, is it creates a separation of charge through a chemical process, but who cares? It creates a separation of charge. And then I come in with this positively charged Q. I don't know what it is. It could be a proton, or it could be some BB that has a net positive charge on it. I don't know. But I put it there, and then I know that this charge Q is going to be attracted to those negative charges. It wants to go down, and it doesn't want to go up, right? So this is a very close, strict analogy to gravitation, the gravitational example that we saw before. If I want to get that charge from the bottom plate to the top plate, I'm going to have to push it and do work on it, and it doesn't want to do it because it has a repulsive force with these charges up top, and it has an attractive force to these negative charges down the bottom. And really, I'm going to have to do work in order to move this through the space in between these separation of charges. So in that process, what we're going to define here is that this charge, because I have to do work on it to move it, I'm giving it some kind of potential energy because it wants to get back to where it started. It wants to get back down to those negative charges at the bottom where it's comfortable and it's more attracted, and away from those positive charges which it's repelled from. And if I think about this, the bigger the charge that I have, if I start out with plus 9 coulombs on this thing, and I feel how hard it is to lift that up, and then I double it and I have 19 coulombs on this charge, or 18 coulombs, I double it and I raise up, I'm going to have to work twice as hard to get it up there. So I conclude very quickly by doing the simple, experiment, that the larger the Q is, the more work we must do, and that work that we do is proportional to the amount of charge. This is not a 9, it's supposed to be a small q. It's the amount of charge on the, whatever this object is. So the potential energy is going to be proportional to the amount of charge. That's my first conclusion. Let me, as normal, what's the symbol on the left? Oh, delta U. So U is going to be my, Brian Griffin asked, what's the symbol on the left? The symbol on the left, I assume, Brian, that you're asking, is this U. The U is going to be our symbol for the gravitational, the electrical potential energy, just like U before was potential energy in gravitational or in springs or anything like that. Usually U is reserved for potential energy. The delta is Greek symbol delta. And for whatever reason, over the years, the convention is delta is the letter of change. So what this is shorthand for in Greek would be the change in potential energy. And basically the difference between the final potential energy and the initial potential energy. And if you bear with me, first I have something in my throat, and but I'll explain this in a minute. And the symbol in the middle, yes, the symbol in the middle, as you surmised, is the proportional symbol. Sorry, I've been using these stupid Greek symbols for so many years that it's like, the regular alphabet to me. You're absolutely right. This is a new symbol that I don't use very often. It's not a fish. It's not a duck puckering out its lips. It is a proportional symbol. I think it is, I don't know if that's a Greek symbol or not, but it basically means proportional to. So what we're saying here is that potential energy is proportional to the charge. Okay, I could have just said that. This is a symbolic way of noting that. So we're at the midway part. Let me stop the recording again so I can split the files.